All right, good morning. Welcome to lecture cycle 10. We're almost at the end of this class. We have lecture this week, we have lecture next week, and then that's it. We'll have like some a help session before the final. So this today's class, and actually this whole week, I guess, is largely concerned with the evolution of social behavior, the evolution of cooperation, and the evolution of behaviors that seem to be altruistic or self-sacrificing. And this whole area represents sort of, when Darwin was working out his theory of evolution by natural selection, this was a really puzzling aspect for him, because up until this point in this class, we have been defining fitness as sort of a competitive process, right? So how do we calculate the relative fitness of an allele? Well, it's the fitness of this genotype divided by the fitness of who's doing the best. Or how do we know whether an allele is going to increase in frequency? As one allele increases in frequency, another allele decreases in frequency. Or how does sexual selection work? Well, individuals of one sex compete with each other. Maybe they actually beat each other up for access to members of the opposite sex, or maybe they compete to be chosen. But a lot of selection is fundamentally competitive, and we measure fitness in this competitive context. And yet, many organisms, I guess these are all animal examples, but all sorts of living things, not just animals, living groups. And many times we see the occurrence of social behaviors between members of the same group. When I talk about a social behavior, that refers to any behavior that's performed by a member of one species and directed towards another member of the same species. So you patting your dog, we don't call that a social behavior because you're different species, but if you share your sandwich with your friend, or you punch somebody else in the nose, I don't know why, those would both be social behaviors. And when we consider social behaviors, we can classify any social behavior according to how it benefits the fitness of the actor. The actor is the individual performing the action, sharing the sandwich, punching the nose, helping the little old lady cross the street. How does it benefit how does it affect the fitness of the actor? Does it increase their fitness or decrease the fitness? And how does it affect the fitness of the recipient? Your friend's fitness maybe increases if you share your sandwich with them. Maybe your enemy's fitness decreases if you steal their earpods. So we can classify any social interaction in this sort of 2x2 framework. Does it benefit the fitness of the actor? Does it benefit the fitness of the recipient? Does it harm the fitness of the actor? Does it harm the fitness of the recipient? And so some behaviors, like cooperative hunting in large mammals, are going to benefit both the actor, the individual performing the action, and the recipient. So a wolf will share its meat with another member of the same pack, and that will help them both to survive, and then they can both cooperate to hunt like a bigger prey item than either one could on their own. So some behaviors benefit the actor and also benefit the fitness of the recipient. There's also a lot of behaviors that benefit the fitness of the actor but harm the fitness of the recipient. And so an example of this type of behavior would be infanticide in lions. So many of you have seen the documentaries, and you know that lion prides, they're mostly composed of lionesses, the female lions, and their babies, but there's often like a male sort of associated with the group, with the pride. Sometimes a new male will come in, beat up or chase away or kill the old male, and then the first thing the new male does is to kill all the babies. the babies that were sired by the other guy, by the previous male. Now clearly, so why would he do such a thing? This clearly decreases the fitness of the babies. They're dead now. However, it increases the fitness of the infanticidal male. And the reason for that, of course, is that by killing the babies, it brings the lionesses who were like nursing and lactating, the lionesses will now very rapidly come back into estrus and be available for mating. And so it increases the fitness of the individual that murders these baby lions. I would like to give you an example of a behavior that belongs here in fitness space, a behavior that is costly to the recipient and also costly to the actor. But the fact is, there are really no good examples of behaviors like that that occur in natural populations, except maybe in our own species, but humans are weird. So imagine, I don't know, I mean, this is just a hypothetical. It doesn't actually happen, but imagine a squirrel gets a grenade and it jumps into a burrow full of other squirrels and it blows up the other squirrels, decreasing their fitness, but it also blows itself up, decreasing its own fitness. This doesn't really happen in the natural world, so we won't worry about it too much. But here, this part of fitness space is really where we are puzzling over at the start of today's lecture. So there's lots of behaviors. Okay, so this is sensory behavior in meerkats. So meerkats live in a group. These are like small mammals that live in Africa, and they live in a group, and some individuals will just spend almost all their time just scanning the horizon for predators. And they'll warn the other members of the group if they see something approaching. And obviously this is good for the other members of the group because you have somebody that's looking out for you, that has your back. It's less easy to see how this benefits the fitness of the actor, of the individuals performing the sentry duty. This seems to be a self-sacrificing behavior. They are spending so much time on sentry duty that they don't have very much time to eat. They are missing out maybe on mating opportunities. This seems to be costly to the fitness of the actor, even though it helps the fitness of the recipient. So we have names for these four classes of action, and so we call them cooperation, selfishness, spite, which we almost never see in the natural world, and altruism, the problem of altruism. So anything in this top row, anything that benefits the fitness of the actor, that's cool, that's fine. It is easy to see how behaviors that benefit the fitness of the actor have been favored by selection. Okay, why has cooperative hunting in wolves been favored? Well, because individuals that hunt cooperatively have higher fitness than individuals that don't. Why has selfishness, like infanticide, evolved in lions? Because male lions that do this have higher fitness than male lions that don't. So anything in the top row is very easy to reconcile with how we think selection works and how we think fitness works. So that's no problem. I guess spite is also no problem. If there were lots of examples of this spiteful behavior, organisms doing things that reduce their fitness but also reduce the fitness of other individuals, then we'd have to explain it. But as I said, this is vanishingly rare. It basically never happens, so there's really nothing to explain. What we do need to explain is the so-called problem of altruism. How can behaviors persist if they reduce the fitness of the actor? Because unlike spiteful behaviors, which I can't really come up with any real examples of, apparently altruistic or self-sacrificing behaviors, things that seem to reduce the fitness of the actor, the individual performing the behavior, and increasing the fitness of the recipient, traits like this are very, very widespread. And all of my examples in this class are going to be from animals, but there are examples of apparent altruism in all the taxa in plants, in bacteria, in fungi, lots of groups. So here are just some examples. So on the left, we have this is a venomous snake here. I don't know what kind of snake it is, but these birds are called babblers. They live in the Middle East. They breed in a group, and there's a lot of poisonous snakes in the area that these birds breed in, unfortunately. And so whenever a poisonous snake approaches, some of the adults will rush over and do what we call predator mobbing. They come very close to the predator. They try and scare it away. Sometimes they scare it away. Sometimes the predator just kills them. And so this is a potentially very costly behavior. Individuals that engage in this behavior are less likely to survive than individuals that don't. But it benefits the fitness of, or it benefits the fitness of other individuals in the group. Yeah, sentry behavior in meerkats or prairie dogs, which I think these guys are, is another example. So maybe you are risking your life or passing up opportunities to forage, to eat for the benefit of others. Why would that be favored? And likewise, there's also reproductive altruism. So maybe you are passing up opportunities, maybe you're not directly risking your life, but you're passing up opportunities to reproduce. And that also seems like it should be a really terrible idea. How could selection favor that? So you're probably all familiar with the existence of like sterile workers in the social insects, like termites and bees and wasps and ants. There's whole classes of individuals that just never reproduce. Worker bees, for example, will spend their whole lives just helping their mother, the queen, produce more and more and more bees. They never attempt to reproduce on their own. And how could selection favor something like that? Or in birds, there's a somewhat less extreme example called helping at the nest. So these birds are called bee eaters. That's just the name of the species. And in bee eaters, when a young bird becomes independent, it leaves the nest, it doesn't necessarily leave the territory. It doesn't necessarily go on and get its own territory and try to attract a mate and produce babies of its own. Very often in these birds, once an individual grows up, it will just stick around mom and dad's territory and help its parents produce new eggs and new babies, instead of reproducing on its own. Reproductive altruism. Why would you ever pass up a chance to reproduce? Why would you ever pass up a chance to get your alleles into the next generation? Okay, I just want to point out that a lot of the apparently self-sacrificing behavior that we see that you might think of as altruism is not actually altruism, but cooperation. So parental care, or even grandparents providing care or help or defense to their grandchildren. Anytime an individual is providing care or help to its direct descendants, that's not a problem for selection theory, okay? This makes sense. Parental care is not a form of altruism, but really a form of cooperation. So when this tiger feeds its baby or protects its baby from predators, yeah, it's improving the fitness of its offspring, but it's also improving its own fitness, because that baby is how the tiger gets its alleles into the next generation. So parental care is not really a big problem for selection theory. Parental care is not part of the problem of altruism. Same for the penguin. Penguins are awesome, wonderful parents, but that makes sense. This increase, so providing parental care or incubating your baby penguin egg improves the fitness of the recipient, of your offspring, but it also improves your own fitness. What is more challenging to explain is why individuals might reduce their own survivorship or reproductive output in order to help individuals that are not their direct descendants. And so ground squirrels, for example, are another species that spend a lot of their time just sort of looking around for predators. And adult female ground squirrels, if they see a predator, so a coyote or an owl or a hawk, they will just start screaming. And then all the babies on the meadow will like bumble around, but eventually like dive into the burrows. This puts the adult females that are producing these alarm calls, it puts them at risk, it makes them more visible to the predator. And adult female ground squirrels will do this even if they don't actually have any babies of their own. Even if they don't have babies on the meadow at that time. So they are, they're helping out other individuals in the group, but they are not their direct descendants. And same with the bee eater birds. They are helping out individuals who are not their direct descendants. In the case of the bee eaters, they're helping their brothers and sisters. Relatives, but not descendants. And so, once again, the question of altruism is how could selection ever favor a trait or a behavior that reduces the lifetime reproductive success of the actor, whether you're taking risks with your life or you are passing up opportunities to reproduce? Doesn't that fly in the face of everything we know about how fitness works? Okay, for a long time, so Darwin realized that this is a problem and really wrestled with it. But early in the 20th century, until about 1960 or so, most scientists, most evolutionary biologists would have said, well, it makes sense for things to behave in this self-sacrificing fashion because individuals should sacrifice themselves for the good of the species. And maybe you've seen like these old nature documentaries like The Wonderful World of Disney, and there'll be lemmings running off a cliff, throwing themselves off a cliff, and the narrator will say, well, the population was approaching too high to the environmental capacity, and so the lemmings knew to sacrifice themselves for the good of the species. We now formalize this idea and call it the idea of group selection. Group selection is the idea, it kind of makes sense on the face of it, that if we have a population or a group or a species that is made up of individuals that are helpful and cooperate and nobody takes more than their fair share of the resources, that population is probably going to do better, going to stick around for a longer time than a population where everybody's fighting and backstabbing each other and behaving selfishly. So that's the idea of group selection, that groups composed of helpful individuals do better than groups composed of selfish individuals. The problem is that it really just takes one individual, one selfish individual to stumble into this really nice, kind, cooperative group, and then that selfish individual is just going to make it like gangbusters. They're going to do great. And so those selfish alleles are going to spread very rapidly throughout the group. We sometimes call this the free rider problem. And if you've ever been like part of a group project where most of you are working really hard and trying to get your assignment done to your instructor's specifications, and one person just never shows up and doesn't do the work, you're sort of familiar maybe already with the free rider problem. So group selection does not seem to be a strong enough force to explain the tremendous extent of apparently altruistic traits. So instead of group selection, we now think that these self-sacrificing behaviors are, at least sometimes, favored by what we call kin selection. And before I explain to you what kin selection is, we have to just sort of reframe how we think about fitness. So up until now, I've been telling you to consider fitness as, how many offspring do you produce, or how many eggs do you lay, or maybe how many grandchildren you have. But the way to be fit is to reproduce, and the more you reproduce, the fitter you are. That's how we've been thinking of fitness up until this point. It's all about getting your alleles into the next generation. And reproducing is a great way to increase your fitness, but it's not the only way. We can think of producing offspring of your own that is actually direct fitness. So we can call that direct fitness. And yes, if you produce offspring, you are getting your alleles into the next generation. But another way you can get your alleles into the next generation is to think, okay, yeah, I've got these alleles, and I'd like to get them into the next generation. You know who else has these same copies of my alleles is my brother, or my sister, or my cousin. So your relatives have a lot of the same alleles that you do. And so things that you do that help your relatives, your non-descendant relatives, to reproduce, that is also a way that you can get your alleles into the next generation. And we can call this indirect fitness. So any additional offspring that your non-descendant relatives can produce as a result of help that you give them, those contribute to your indirect fitness. And so kin selection theory simply says it's not enough just to look at direct fitness. We really need to consider both of these. And so instead of just taking a really narrow view and looking at direct fitness, counting up how many offspring you reproduce, we also take into account the indirect fitness. We add direct and indirect fitness together. And the really important quantity is the inclusive fitness, your direct fitness plus your indirect fitness. And so kin selection favors helpful behavior that is directed towards your relatives, so long as that helpful behavior causes your inclusive fitness to go up. Okay? So your direct fitness is going to go down, but so long as your indirect fitness goes up by more than the hit to your direct fitness. In other words, as long as your inclusive fitness is increasing as a result of you performing the action, then that helpful behavior, that action is going to be favored by kin selection. With me so far? Okay, because we can get quantitative with this, and this idea was formalized by Bill Hamilton in Hamilton's rule, which is just this super simple little inequality here: RB is greater than C. Any helpful behavior, any helping your relatives at some cost to yourself, is going to be favored by kin selection so long as this is true. So what's R, and what's B, and what's C? B is how much your help benefits your relative. Do you help them a lot? Do you save their life? Do you help them produce like 100 extra offspring? Or do you help them just like a little bit? That's what this B represents. R represents the coefficient of relatedness between the helper and the individual getting the help. How closely related are these two relatives? Are they very closely related, like two brothers that have a coefficient of relatedness of like 0.5? Are they more distantly related? So you and your cousins have a coefficient of relatedness of 0.125. R is always somewhere in between 0 and 1. And the closer you are to 1, so your coefficient of relatedness to your identical twin, if you have one, is 1. Your coefficient of relatedness to yourself is 1. But any other individual in your family, your coefficient of relatedness is somewhat lower. In the textbook, the assigned rating has some information about how to calculate coefficients of relatedness. But anyway, R takes into account that some relatives share more alleles with you than other relatives do. And so it might be more efficient, for example, for you to help your sister than for you to help your second cousin twice removed, because you actually share more alleles with your sister than with a more distant relative. So R times B, how much you're helping the relative weighted by how closely related you are to that relative, is R times B greater than the cost to yourself, the cost to the helpful individual. And if R times B is greater than C, then kin selection predicts that, yeah, this behavior should be favored. This behavior, helping this relative, will increase your inclusive fitness. In other words, this is no longer altruism, this is cooperation, as long as we define fitness as your inclusive fitness, not just your direct fitness. Good so far? Okay, because it's a very different way of thinking about fitness, but it solves the problem of altruism because it shows that behaviors that satisfy this, helpful behaviors directed towards relatives, so long as R times B is greater than C, these helpful behaviors, even though they decrease your direct fitness, they increase your inclusive fitness. And so we're not dealing with that bottom left quadrant. We're not dealing with altruistic behaviors. Kin selection is a form of cooperation. Yeah, and here's just a little quote. Would I lay down my life to save my brother? No, but applying kin selection theory and knowing that you're related to your brother by a coefficient of 0.5 and your cousins by a coefficient of 0.125, it would be worth it to sacrifice your life for this set of relatives. Okay, so let's work through an example. Imagine that you have the opportunity. This is sort of like a trolley problem. A lot of these kin selection questions are sort of like the trolley problem in philosophy, except you're maybe faced with the question of, should I sacrifice my own life in order to save the lives, say, of a bunch of relatives? So just a reminder that you are related to your first cousins by a coefficient of 0.125 and to a half sibling, somebody with one of the same parents but not two, by a coefficient of 0.25. If this many of these relatives are about to die and you have the opportunity to sacrifice your own life to save their lives, does kin selection predict that you should do it? According to kin selection, should you sacrifice yourself? So the cost to yourself, so is RB greater than C? Well, the cost to me is one life, is my own life. So what's R times B? Well, for the cousins, we've got my coefficient of relatedness to them times how many there are. And we've also got some half-siblings with this coefficient of relatedness times how many there are. And so I could quickly sketch out on the back of a napkin or smash it into my little phone calculator that R times B is actually greater than the cost to myself. And so according to kin selection theory, yes, my inclusive fitness would actually increase if I sacrificed my life to save the lives of this set of relatives. My direct fitness would go down, sure, but my indirect fitness would go up even more. So inclusive fitness would increase a little bit. So I should do it. Okay, so this is important. Hamilton's rule does not require that helpful organisms are able to do the math. You don't have to be able to do arithmetic and solve this inequality to obey Hamilton's rule. And we actually see organisms obeying Hamilton's rule even if they are plants, or even if they are squirrels or something that can't do, or even if they are birds. What kin selection favors is not actually doing the equation and working out the math and then behaving accordingly. What kin selection favors is the evolution of these sort of rules of thumb or these instinctive feelings that, for example, you grow up with, you spend your whole childhood in the same living area as somebody. And so you feel very protective towards them. You love them. You would take risks to a certain degree to help them out. That's what kin selection favors, not actually doing the math. But the math works out surprisingly well. All right, so here's another species of bird that has the option of helping at the nest. So this is a Florida scrub jay. And in Florida scrub jays, like in the bee eaters, once baby birds sort of reach adulthood, they can either sort of strike out on their own and try and find a territory and try and find a mate and try and produce offspring, or they can just hang out with mom and dad on the old home territory and help their parents. Their parents don't force them or try to coerce them or anything, as far as I can tell. It's just a decision that these birds make or don't make. But according to kin selection theory, say that these are your options. Say that you are this bird, okay? So you can help mom and dad, and if you help them, then they are going to be able to produce like an extra 4 offspring, an extra 4 full siblings for you that that they wouldn't otherwise have been able to produce if you weren't there helping them. So the fitness payoff of that is 4 times how closely related am I to those brothers and sisters I'm helping? 0.5. So 4 times 0.5. That's my fitness payoff for being a helper. But my fitness payoff for just finding my own territory and trying to reproduce, increasing my direct fitness, is 3 offspring. Now, how closely related am I to my offspring? Well, my coefficient of the parent-offspring coefficient of relatedness, again, you'll remember this from the book, parents and offspring are related to each other by 0.5. And so you see the fitness payoff of this, of increasing my direct fitness, is actually 3 times 0.5. It's only 1.5. So there's a better fitness payoff for helping and passing up a reproductive opportunity of your own under this circumstance than there is for going it alone. So in this case, kin selection would favor passing up a reproductive opportunity and instead staying home and helping. But there are other populations of scrub jays where the 2 parents don't actually stay together usually. After they produce offspring, then they both swap out, find a different mate. Now, individual birds can still help their parents, but their parents are no longer together, and so they can help one of their parents. Maybe they can stay in their mom's territory, but she's got a new baby daddy now. So you can help your mom and your stepfather produce relatives for you, but these are not going to be your full siblings. You're not going to be related to them by 0.5. They're going to be your half siblings. You will be related to them by 0.25. And so again, you can produce you can help to produce 4 individuals that are related to you by 0.25. So this fitness payoff is 1. Your other option, again, is to find a mate of your own and produce 3 offspring. You are still going to be related to your own offspring by a coefficient of 0.5. And so you see the fitness payoff of producing your own babies, in this case, is higher. So kin selection does not favor helping at the nest in this situation, even though it did in the last situation. And well, actually, scrub jays are pretty smart, but they probably can't do the math. They have been selected to behave in this way. Birds in populations where males and females stay together for many years are much more likely to help at the nest than birds where their parents choose new mates every year are. So they obey Hamilton's rule. I don't think they're actually doing the math, though. Okay, so kin selection favors helping out your relatives a lot of the time, and the reason, and the closer related you are to those relatives, the more likely it is that kin selection will favor helping them, even at some cost to yourself. And this is because you have overlapping genetic interests with your relatives. And the closer relatives you are, the more your genetic interests overlap, the more alleles you have in common. So you're more closely related, you have closer genetic interests, more similar genetic interests with your sister, for example, than with your second cousin. Because you share more alleles with your sister than your second cousin. So genetic interests overlap within a family, but genetic interests are almost never the same within a family. So even though you're super closely related to your sister and you do a lot to help her out, you are more closely related to yourself than you are to your sister. Your coefficient of relatedness to yourself is 1. Your coefficient of relatedness to a full sibling is only 0.5. And this results in genetic conflict. There can be disagreement even within a family group, even within a bunch of very close relatives, about how much parental care is appropriate to provide, or there can be conflict between siblings, sibling rivalry, for example. Maybe this bird can only catch like 50 crickets in a day, and maybe these two individuals, even though they're siblings of each other, they might disagree, they might squabble over how many of the crickets go to this little greedy guy or this little bum that's getting stepped on. So there are these asymmetries in relatedness. You're always more closely related to yourself than you are to anyone else in your family, unless you have an identical twin. But most of us, we're more closely related to ourselves than we are to any other relatives. And these asymmetries in relatedness can introduce genetic conflict or disagreement as to how much help an individual should be providing to another relative. So let's revisit Hamilton's rule. A helpful behavior increases the fitness of the helper, the inclusive fitness of the helper, so long as this is true, so long as R times B is greater than C. Hamilton's rule, like this, is framed from the perspective of the helper or the actor, the individual that has the option to help their relative. So the focal individual here is the one that is contemplating whether to help or not. But we can make it more general. And if we make it more general, we can look at what's the desired outcome, not just from the perspective of the helper, but also from the perspective of the family member that wants to receive some help, or the perspective of another individual in the family that's related both to the helper and the recipient. We can make it more general and rewrite Hamilton's rule, say that helpful behaviors increase the inclusive fitness of anybody in the family. We're no longer restricting ourselves to having the helper as the focal individual, so long as R sub 1 B is greater than R sub 2 C. So what's R1 and R2? R1 is the focal individual, the individual who we are now asking, should someone help or not? The focal individual's relatedness to the recipient, to the individual that gets the benefit. And R2 is how closely related is the focal individual to the helper. Okay, so in sort of regular Hamilton's rule, the focal individual is the helper, and so R sub 2 is like equal to 1 because they're related to themselves 100%. B and C are still what they were before. How much does the recipient benefit? How much, what sort of cost to the helper's direct fitness are we looking at? So let's imagine the situation that you have a brother, and so it's a full sibling. He's a full sibling to you, so your coefficient of relatedness is 0.5. And you have the opportunity to help him, and if you do, it's going to cost you 10 of these arbitrary units of fitness. So the cost is 10. And my question is, what benefit to your brother makes this worthwhile from your perspective? Okay, so from the point of view of the helpful individual, how much of a benefit to my brother am I going to expect for it to be worth it to provide this help? So, okay, again, here's the more general form of Hamilton's rule. So R sub 1 is how closely related are you to your brother, so 0.5. We're trying to solve for B, But R sub 2, how closely related are you to the helper? How closely related are you to yourself? So that's 1. And the cost is 10. So we can just rearrange this inequality, divide both sides by R sub 1. And you can see that it's only worth it from your perspective to incur a cost of 10 if your brother benefits by at least 20. Okay, so if the benefit to your brother is greater than 20, then yeah, your inclusive fitness is going to increase by you providing this help. So from your perspective, you're going to help you might want to help your brother. You have overlapping genetic interests with your brother because you have some of the same alleles. But your brother is only half as important to you as you are to yourself. From your point of view, you are twice as related to yourself as you are to your brother. And so if the cost to you is 10, then you want to see a benefit of at least 20 to your brother. Otherwise, it's not worth it from your perspective to help your brother. But imagine I asked your parents, should Bio 1001 student be helping their brother? This is the cost to them. Under what situation, under what conditions should they be helping your brother? From the point of view of your parents, they love you both the same. And why do they love you both the same? Because their coefficient of relatedness to you is exactly the same as their coefficient of relatedness to your brother. So you are both equally valuable to them. And so from the point of view of your parents, what's the minimum benefit to your brother that would make them want you to help him? Just yell it out if you know. 10, yeah. So long as the benefit to your brother is greater than 10, then your parents should be encouraging you to pay that cost of 10. Because they are equally closely related to both of you. Whereas from your point of view, no, you're twice as related to yourself as you are to your brother. You're twice as important. What about the point of view of your brother? Well, your brother is twice as, his coefficient of relatedness to himself is 1. His coefficient of relatedness to you is only 0.5. And so from the point of view of your brother, under what circumstances should he be hoping that you'll help or be asking for you to help? What's the minimum benefit that your brother would get? 5. Thank you. Thank you for the bold voice there. And you're exactly right. Your brother is going to help anytime the benefit to him is greater than 5. Okay? And so you see here that in this zone, if the benefit to your brother is, say, 7 or 11 or something, there's going to be family conflict. Your brother is going to be knocking on your door asking you for help, maybe anytime B is greater than 5. Your parents will be hassling you to help your brother anytime B is greater than 10. From your perspective, it doesn't make sense you don't benefit by helping your brother unless the benefit to him is greater than 20. So anywhere in between 5 and 20 on this slide, there's going to be family conflict. There's genetic conflict because everybody on this slide is related to each other, but there's asymmetries in relatedness. And this is why we get genetic conflict even within family groups. And the most intense conflicts turn out often to be within family groups. However, if the benefit to your brother is super, super minor, then there's no family conflict. The benefit, your brother would benefit a tiny little bit for you to take this big risk. But even your brother would agree, no, don't help me. I got this. I'm good. And likewise, that there's no conflict if the benefit to your brother is greater than 20. Then everybody on this slide is going to say, yeah, the cost to you is really a lot smaller than the benefit to your brother. You really should be helping him, and you would agree with that. So we get conflict in the intermediate zones and agreement if the benefit is either very, very small or very, very large. Okay. Got a bunch of clicker questions. We'll probably just be able to get through one and then take it up, but we'll carry on with that. Okay, so imagine now that you've got a half-sister. So you and your half-sister have the same mother, but you have two different fathers, and you have the opportunity to help her. Here's your coefficient of relatedness to her. You can help her, and it would benefit her this much. How much of a cost to your own direct fitness are you willing to bear to help her out by this much? So here, the focal individual is you. From your perspective, how much of a cost is worth it? This is how much she's related to you. The benefit to her is 20. And you'll notice that you are 4 times more related to yourself than you are to her. Okay, that's a good chunk of the class answering. Nice, okay. B is the correct answer here. And let's just take it up, good job. Okay, so from your point of view, you are the focal individual, and you're asking is R sub 1, so is my relatedness to her times the benefit greater than my relatedness to myself times the cost. So R sub 1 is 0.25. R sub 2 is your relatedness to yourself. So helping your half-sibling increases your inclusive fitness. If this is true, 0.25 times 20 is 5. Only if it doesn't cost you more than 5 of these arbitrary fitness units would that be worth it from your point of view. And next class, we'll pick up where we left off and start to look at this from the point of view of other individuals in the same family. And spoiler, there's going to be family